I'm going to talk a little bit more about complex numbers. We're first going to start by graphing complex numbers on a complex plane. So this is going to look super similar to graphing an x and y ordered pair. The x-axis is our a-axis or our real axis. And the y-axis is our b-axis or imaginary axis. And again, this is coming from the complex number a plus bi. So if I want to graph -3, think about it as -3 plus 0i. So -3 still works the same way. -3 is the real component. Negative is left, positive is right. So I would go to -3. And I'm not going up or down at all because it's 0i. So this one is going to be, and I'm going to label it with a capital A so we know that that is the point I'm talking about. This one, I have an imaginary component, so it's 0 minus 3i. So 0 means I don't go left or right at all. And I'm going to go down 3 on the imaginary axis. So this is B here. Okay, C, 4 plus 3i. So I'm going to go right to +4 and then up 3 in the imaginary direction. So this is the C complex point. And then D, I would go -2 on the real axis and then +4. 1, 2, 3, 4. So this would be that point D on the complex plane. So really similar to graphing x and y, just knowing that the x-axis is our real component and the y-axis is our imaginary component. Okay, so we're gonna talk about what the absolute value of a complex number is. So remember, absolute value is defined as the distance from 0. So if I were to graph the point 3 plus 4i, again, if this is my real axis and imaginary axis, I would go right 3 and up 1, 2, 3, 4. So that is the point I'm talking about. So the distance from that point to 0, the shortest distance is that straight line distance, right? Well, I can't really count how far that is because it's going partially through those squares, but I could draw in a right triangle, and I know that this leg, it has a length of 3, and this length has a length of 4, and I can use that to find the hypotenuse. So I'm going to use the Pythagorean theorem. So I'm going to say c squared equals a squared plus b squared, right? And c squared being the length of the hypotenuse here. So a squared is 3 squared, b squared is 4 squared. So c squared is 9 plus 16. So c squared is 25. Square root. Now, normally we would have plus or minus, right? But we're distance or measuring is always going to be positive. So +5 is the distance from 0 to 3 plus 4i. So the absolute value of a complex number is just the square root of a squared plus b squared. Okay, so it's essentially just Pythagorean theorem to find that distance. Okay, so here, if we want to find the absolute value, I'm just going to do that. So square root of a squared, so a is -3 plus b squared. So we get 9 plus 25 is 34. So the absolute value of, and I don't think I can break into 2 and 17, but so that is our distance from 0 is the square root of 34. -13, so again, think of that as -13 plus 0i. So you actually don't really have to do the 0, right? Because 0 squared is just 0. So -13 squared is 169. Square root of 169 is 13. So when we're missing an A part or a B part, it's because it's sitting on one of the axes. So then it's just going to be whatever that value is, but positive. Okay, so this one is just going to be 7. But again, if it helps to do it longhand, you sure can. Right, -7 squared, 49. Square root of 49 is 7. And again, we're using positive because we're measuring a distance from 0. All right. All right, the next operation we're going to do, you guys, is And then 2i plus negative 7i is negative 5i. So a plus a and b plus b. That's what we're doing. We're combining a's together, b's together, okay? If you have a minus in between though, remember that's like a -1, so we do need to distribute that first. So we're gonna have, sorry, that keeps blurring. So we have 5 minus 2i, distributing the -1, I have -2 and plus 3i. So like terms, the real components, 5 minus 2 is 3. Negative 2i plus 3i is positive 1i, so plus I. Okay? Again, negative on this one, so let's distribute. So I have 6 minus 3i minus 4 plus 2i. Negative 4 and 6 is 2. Negative 3i, 2i is negative 1i. Okay, here it's addition, so I don't have to distribute anything. So 1 minus 1 is 0. Negative 3 plus 3 is 0. So because the real components were opposite and the imaginary components are opposite, that actually does just equal 0. And 0 plus 0i, I can write as just 0. Multiplication, okay. We are going to use our distributive property just like normal, but anytime I get an I squared, remember that's equal to -1. So I'm going to distribute this here. So I have negative 2i times 2 is negative 4i. Negative 2i times negative 4i is positive 8i squared. So anytime I get an I squared, remember that's -1. So this really turns into negative 4i plus 8 times -1. And -1 times 8 is -8. So writing it in standard form, -8 is the real part, and negative 4i is the imaginary part. Okay? If I have a complex number times another complex number, we distribute twice. So 2 times 4 is 8. 2 times negative 6i is negative 12i. 3i times 4 is 12i. And 3i times negative 6i is negative 18i squared. Okay, so like terms here, my i's, negative 12i plus 2i is negative 10i. And then negative 18, I squared is -1, so that becomes a positive 18. Okay, so I have 8 plus 18 minus 10i. Oh, sorry, did that a little too high. 8 plus 18 minus 10i. So 8 plus 18 gives me 26 minus 10i. Again, I'm just writing it in that standard form, so the real part comes first, then the imaginary part. Okay, same thing on this one, distribute twice. So 1 times 6 is 6. 1 times negative I. 2i times 6 is positive 12i. 2i times -1 is negative 2i squared. Okay, so I have 6 plus 11i, and then -2 times -1 is positive 2. So now I can add the 2 to the 6 and get 8 plus 11i. Multiplying conjugates. So remember, conjugate has the same a and b, but the sign in the middle has changed. So here, 2 plus 3i, 2 minus 3i are conjugates. You might recognize this is actually difference of squares in factored form. So we know a difference of squares comes from this being squared minus this being squared. So if I think about that, a squared is just going to be a squared. But here, this is minus b squared times I squared, right? If I apply that squared to both parts, and I know that I squared is -1. So I get a squared minus b squared times -1. Well, subtracting a negative b squared is really going to change it to a squared plus b squared. So that is the shortcut. So here I can do a squared, which is 4, and then plus b, either 3 or -3 squared is 9. So if we add those in, it's 13. So multiplying the conjugates gets rid of the I term, and we're left with just a real component. Here, if I do that, 4 times 4 is 16, plus -2 squared, or 2 squared is 4. So this one's going to be 20. So we're going to use this idea of multiplying by the conjugates, you guys, to Divide. So we want our solution to be in that standard a plus bi form, and right now it's not. We have I in the denominator, which is not considered simplified. So what we're going to do is we're going to multiply by the conjugate of the denominator. Okay, so if this is 3 minus I, the conjugate would be 3 plus I, and we're going to multiply both the top and the bottom by that, because this fraction then is just equal to 1. So multiplying something by 1 doesn't change its value. It's just going to change how it looks here. So on the numerator, we're distributing, okay? So 2 times 3 is 6. 2 times I is 2I. 3I times 3 is 9I. And 3I times I is 3I squared, okay? Numerator, we're multiplying conjugates together, so we can use that shortcut, a squared plus b squared, okay? So simplifying here, we get 6 plus 11i, and then I squared is -1. -1 times 3 is -3. On the bottom here, I get 9 plus 1. Okay, so lastly, 6 and -3 is 3 plus 11i over 10. You can leave it like this, but you may wonder, wait a second, that doesn't look like our usual standard form. I can break this into 2 parts and say that 3/10 is the real component and 11/10 I is the imaginary component. So those are equivalent. This looks a little more how you're used to seeing it, but leaving your answer in this form is fine as long as there's no I in the denominator. Okay, let's try another one. So conjugate of the denominator would be 6 minus 2I. So we're going to multiply the top and the bottom by that. Okay, on top, distribute. So 4 times 6, 24. 4 times -2I, -8I. -2I times 6, -12I. -2I times -2I is positive 4I squared. Denominator, a squared plus b squared. Okay, so I'm simplifying. I's make -20I there. Oop. So I have 24 minus 20I, and then 4 times -1 is -4. 36 plus 4 on the bottom. So 24 minus 4 is 20. And then on the bottom, 30 plus 4 is 40. Simplifying here, all 3 of those numbers divide by 20. So I can simplify a little further. 1 minus 1I over 2. So this would be our most simplified. And again, I could break that into 2 A and B components, but this is just fine. Okay, this last dividing example. If I think about the number 5i, in its complex form, it's 0 plus 5i. So its conjugate would be 0 minus 5i, or just -5i. So we're going to multiply the top and the bottom by -5i. Okay, distribute on the top. So I have -15i minus 50i squared. Here I can think a squared plus b squared again, so it's 0 squared plus 25 or plus 5 squared. Okay, which is 25. So we're gonna get -15i plus 50 over 25. I can divide all those by 5, and I'm gonna write it in standard form, so I'm gonna put the 50 first. So dividing by 5, 50 divided by 5 is 10. -59 divided by 5 is -3i, and 25 divided by 5 is 5. This table to try and simplify some expressions involving exponents on I. So this table gives us up to 12, but you'll notice it just alternates, right? I, -1, -I1. It's kind of a pattern of 4 different values. Then it repeats, and then it repeats, okay? So we're gonna try and use that to simplify some of these next ones, and I'm gonna leave this table up so we can refer back to it. All right, so negative 6i to the 14th. So I'm going to try and use something in this table to help me. So I know that negative 6 is not really being applied to that exponent. So I want to rewrite I to the 14th using some of these powers, okay? Like, for example, I could write it as I squared to the 7th. There's more than one way to do this too. This is just one example, okay? Because I know that's the same as I to the 14th. Well, why is that helpful? Well, I squared is negative 1. So I get negative 6 times negative 1 to the 7th. Negative 1 to an even power is always positive 1. Negative 1 to an odd power is always negative 1. So this is just negative 6 times negative 1, or negative 6. Okay, I to the 63rd. Okay, so let's see what we can do with 63. How about 9 and 7? Okay, so I to the 9th from our table here is just I. So that becomes I now to the 7th. Okay, well, I to the 7th, we have right here is negative I. Okay, 1/2 again is not really applied to the exponent, so I'm going to work with the 29. Okay, so 29, how can we rewrite 29? So maybe let's do, yeah, it's not a nice number here. Maybe let's do let's break into this. Oh, sorry guys, let me turn that off real quick. Okay, so here I'm gonna do I to the 10th, I to the 10th, I to the 9th. Okay, because those are all values in my table. And 10 plus 10 plus 9 is 29. So I to the 10th is negative 1 times another negative 1, and I to the 9th is I. So I have negative 1 times negative 1, which is 1. 1 times I is I. So this is the same as 1/2 I. Okay, 42. Okay, let's do, goes into 42 nicely. 6 and 7? Sure. I to the 7th, raised to the 6th power, okay? Right, 6 times 7 is 42, so I to the 7th from our table is negative 1, or excuse me, negative I. And negative I to the 6th, we can also think about that as negative 1 to the 6th and I to the 6th, okay? So negative 1 to the 6th is just 1. And I to the 6th from our table is negative 1. So we have negative 3 times 1 times negative 1 is 3. Oh, sorry, kind of got off there. So here, you guys, negative 1 to the 6th, I know negative 1 to any even power is just 1. Negative I to the 6th, I didn't just work with this one because this one is all just I raised to a power, not negative I. So I broke that into negative 1 times I. So that's why I have the negative 1 and the I kind of separately being raised to the 6th. So lots of ways to do these ones. Use this table to help you, but you can break it down using exponent rules and then use that table to help you simplify.